Okay, guys, why don't we go ahead and get going? Still don't know about this weekend. I'm going to find that out like right after this. So, and then I will post a note on my website if I'm going to be around all weekend or if I'm not. If I will be around this weekend, then that includes a review session on Sunday evening. Otherwise, I'll do that review session on Tuesday evening instead. Either way, today I do have to leave at 5, pretty much right on time. If I do a review on Sunday or Tuesday, I might be able to stay a little bit longer. But for today, I've got to kind of stay somewhat on time. So, which is fine. What I am planning to do is just do a bunch of practice problems today. I'm going to basically assume that you guys are capable of learning all the definitions you need, learning the statements of the theorems, and reviewing the proofs. There will be some questions on the midterm. I have not written the midterm yet, but I can tell you there will be questions on the midterm where it just simply says, give me the definition of this. State this proposition. State this proposition, or fill in a blank. If you look at the sample exam that I posted, one of the pages of those problems, it was almost like 20 points of the test, was just filling in the blanks. So it made it really easy. You just put in fill in the right word, fill in whatever the statement is that you need. So when I write those kinds of questions for the test, right? When I write those kinds of questions, I'm thinking of those as like the easy questions. Like everybody who has studied well and really taken my flashcards advice seriously or whatever, and got those things written down should get all of those points. And you want to be getting all of those points. So those are the easiest things. And there will be a lot of that kind of stuff. Then I'm going to ask a number of other problems that are probably on the easier side of the homework type of difficulty, stuff that would be a little bit easier than some of the homework problems. And then there might be one or two questions that is moderate in difficulty, where it might take a little longer to write it out, or you have to remember something, whatever it might be. But I won't try to do too much of that kind of thing. It's going to be more on the easier side of the stuff you've looked at. So you have the quiz as an example of kind of the sorts of things I think is reasonable. Okay, obviously this test will be longer than that, but it will be, it gives you an idea of kind of the style and the format, that sort of thing. On the day of the test, if you can get here a little bit early, get here 5 minutes early or whatever, if you can stay 5 minutes late, I will give you as much time as I possibly can to take the test. I know it's frustrating to be feeling rushed sometimes with these things. So come a little early, prepare to stay a little late. I can't give you a lot of extra time because there's classes before and after. But I'll give you as best of time as I possibly can for the test that day. Right, so that's mainly my advice. I have, of course, the sample midterm and the solutions and some additional practice problems that are already posted. I'm going to be posting this video as well if you want to watch that again later on. It should give you some ideas about what I'm going to ask you about. Okay? Does anybody have any questions about the format? The test will be a few pages long, fronts and backs. By the way, when I'm looking at how many points the questions are going to be worth, it is not based on how hard the problem is. It is based on how much work you have to do to solve the problem. So it might be a relatively straightforward problem, but you have to write out a lot. Well, that might be worth a lot of points. There might be another problem that there's a little bit of an element of trickiness to it, but it's very short, and so it may not be worth very many points. Usually, if I do write anything that's more on the moderate level of difficulty, I tend to make those worth less points than the stuff that's easier. Obviously, fill in the blanks is not going to be worth that many points, some of the definitions and stuff, but you kind of get the idea there. And if I only give you like 1 inch of space to write an answer on the paper, because I've got multiple questions there, that should tell you something, right? It must not take a lot of writing if he's only giving us a little bit of room. So these are clues that you can take advantage of on the test that will hopefully help you to see what's going on. I like to ask test questions that have parts that are broken down into small pieces, because if somebody blanks out on one thing. I don't like that to be a huge thing. You know, everybody can sometimes forget something. So I try not to do that. So there will be a lot to do. My tests tend to be long. That's why I'm saying try to come a little early, be prepared to stay a little bit late so you can have as much time as possible. Because I get excited about math and I want to ask about everything. And I know I can't do that, but I still try to push it as best I can. So it'll be several parts and several, I don't know how many questions it's going to be, but you know, by the time you add up all the parts, it'll probably be quite a few. Okay, so just kind of be prepared for that. So my plan for the review then was to kind of go through some example practice problems of things that are kind of like what I could ask you, okay, for the test. And it will help us to review some concepts at the same time. Does that sound like a plan? Instead of me just like rehashing all the material again, which is in your notes and it's in the book, I think practicing it, using it, seeing what the problems might be like, might be a better use of our time. Okay, does that sound good? And feel free to interrupt me with questions as we're going along here. Take the liberty to ask me things about this because this is a good chance to do that. I think everybody here wants to learn, and you know, the more interaction we have going along, the better. And I'm going to be asking you guys questions too. I'm not just going to stand up here and solve everything. Okay, so let's do some practice problems. Okay, so here's some examples, and these are all going to find their way up onto the internet, but not necessarily in this order. So just keep that in mind. Okay, so the first one is true or false. And by the way, I will not do that to you on the actual test. So I will not make you answer a true-false question. I will tell you, this is true, prove it, or this is not true, give me a counterexample, because I just think it's under the pressure of an exam that's asking a lot to put people through the mind games. So I won't do that. Okay, so here's the true or false. Here we go. Part A, let f from R to R be a function if A is a subset of R and it is dense. So if A is dense, then f of A is dense. So this is a function, the inputs come from the real numbers, the outputs come from the real numbers, and the question is, if you start with a dense set, is the image of a dense set still dense? This is the sort of thing I would ask, right? How does some property that we learned about, how does it behave with respect to a function? Images, or I could do pre-images as well, but here I'm doing images. So, does anybody have any intuition about this? False. Think it's false? So if you think it's false, then you have to give me a dense subset of R, such that after you apply the function to everything in that subset, you have something that's not dense. So, can you give me an example?
F of Q equals 0.
Okay, so the theory here is that this is false. So you have to define a function from R to R. So we need a formula for f of x. So
X or interest equals 0 for all x's.
how about that? Okay, we're starting off a little bit easy here, guys. Okay, look at that, guys. Every single input spits out 0. So then, of course, f of capital A is just 0. And that is not dense in R. Doesn't even matter what capital A is. So I think, Charles, you were using capital A to be equal to Q.
Yeah.
Obviously, you have to be thinking about what sets do you know that are dense in R. And a great example is Q, right? Classic example of a set that's dense in R would be just Q. So we could take A equal to Q. The image of Q is just 0. So this one, what you would say here, if you were writing this up on a test, is you would say A is dense by a theorem in class. You don't have to know the numbers of the theorems, guys. You just have to know it was from some result from class. So A is dense by a theorem in class. And the set 0 by itself is not dense. can we give just a quick reason? Remember what dense means. Dense means in any interval, and the real numbers, an element of your set would be inside that interval. So turn that around. If something is not dense, the logic of that would be what? The logic of not dense would be that there exists some interval that fails to have any of these elements in it. Okay, and what would be an example of an interval that you could use that would demonstrate that? Anybody? Give me an interval that doesn't have
1, 2.
There you go. It doesn't have 0 in it. So how about this? Here's an interval, 1, 2, contains, well, let's just write it this way. The interval 1, 2 intersected with f of q is empty. So f of q has no elements in the interval 1, 2. As long as you give me an interval that doesn't have 0 in it, you'll be fine for your example. Does that make sense? Not dense. So, pretty easy. Here's 0 right here. I'm going to come up with an interval that doesn't have any points of the set inside of it. Pretty obvious. Okay? Everybody feeling all right about that example? Okay, perfect. Okay, there's a second part to this. I did ask about the preimage. Okay, so part B. If B is dense in R, then the preimage of B is dense in R as well. So this is also true or false. It's just the second part to the same question. So if we took, I'm sorry, this is supposed to be dense here. If B is dense in R, then the preimage of B is dense in R. So that's just a short way to write the question. So if we have a subset of the codomain that is dense, would any preimage of it have to be dense? So you have to think about, of course, what subsets of R do you... you have to think, what subsets of R do you even know that are dense? Of course, Q. Q is one example. What other subsets of R would be dense? An interval?
Yeah.
I would say that the interval from 1 to 2 is not dense in R. Because here's 1 and here's 2. I can come up with some interval on the real number line that has nothing in common with this interval, namely 3, 4. So intervals are not dense. Intervals are not dense. But what else do we know is dense besides just Q? R minus Q, the irrational numbers. Exactly, that was one of the ones in the homework. So the rationals are dense, the irrationals are dense. Anything that is a superset of either of those would also be dense, right? So if I take Q and then I make it even bigger, still dense, right? If you take a dense set and make it larger, it only gets more dense, right, intuitively. So any superset of either Q or R minus Q, and that would include all of R itself, too. So we know quite a few dense sets. Okay. So you could think about defining a function that somehow, focused on whatever that subset B was that you're working with. So I've been blabbering on here for a minute. Does anybody think they have an idea if it's true, if it's false? Think it's false? I shouldn't do this to you because I told you on the test I'm not going to do this to you. I'm going to tell you whether it's true or whether it's not true. So if it's false, we need a counterexample. So we need a function, and then we need a b, and then we have to calculate the preimage of b. So what would be a good choice for, let's start with b. What dense subset of R? We've mentioned several. What dense subset of R would you guys like to work with? You may not have your whole example figured out yet, but what would you like to try? R minus Q. Okay. R minus Q. Perfect. So that's dense, and so that's the irrational numbers. Okay. So now we have to define our function somehow. Okay. Does anybody have a suggestion how we could define it? Of course, we want to make it very simple. You never want to make it very complicated. I'm never going to be asking you to do something really complicated. A simple example is always the best. So remember what the preimage of B is. That's going to be the subset of R that maps into B. So it's going to be those inputs that spit out an irrational number. And if we're saying that this is false, we don't want there to be very many inputs that spit out an irrational number because we want a non-dense set for this preimage. So, have an idea? 0. Well, 0 times anything is just 0. So is this 0? Does that work? So what is, if this is my function, which inputs into this function will spit out an irrational number? Nothing. Nothing. With this example, the preimage of B is empty. There's no element in the domain that's going to spit out an irrational number because they're all going to spit out 0, which is a rational number. So there you go. This is as far from being a dense set as you could hope for. It's a perfectly good example. It works. Yeah, exactly. Now, honestly, my example, if I had done it, I would have chosen Q here. If I did that, you know what I would have done for my function? I would have done that. Because now the preimage of the rational numbers would have been empty again. Because nothing is mapping to a rational number. They're all going to an irrational number. Okay, so that's one way to do this. Kind of play around with it a little bit. Okay, everybody all right with that example? Okay, let's go on. So just wanted to go over density with you a little bit. Let's take another problem here. Let's talk about countable and uncountable. Let's kind of practice a few of those examples again. So this is the second example. Decide if these are countable or uncountable. Now this also, it almost sounds like a true-false question. True or false, it's countable. But I might ask you, in something like this, I might ask you to actually make the determination of whether it's countable or not. Okay, so I'm going to give you a few examples of this. Here's the first one. Let's take S to be the set of m over 2 to the k, such that m is an integer and k is a natural number, union with the set of m over 3 to the k, such that m is in Z and k is in N. And the question is, would that be countable or uncountable? Countable? Everybody agreeing with countable? All right, I agree as well. This is countable. Now, what would be... You're never going to be able to just give me an answer. I'm going to have a reason. How would you justify it? This is a subset of Q. It's fractions, right? Another subset of Q. So actually this whole union, this whole set S is actually a subset of Q. Okay? So we could just say that. Since S is a subset of Q, and Q is countable. And you can just say from class. So from class, then S is countable by a proposition that we learned in the book. I think it was 2.11. But again, you don't have to know the numbers. So a subset of a countable set is countable. That's all you have to say. There were a number of people on the quiz who were citing that big theorem 2.4 about a countable union of countable sets is countable. And you know what I saw people writing on their quiz? They were careless. They said a union of countable sets is countable. That is not true. A countable, you have to say every word exactly right. A countable union of countable sets is countable. If you leave off the word countable anywhere in there, then you're saying something nonsense. Right? And I can only go off of what I read. So please, if you're going to write out statements of anything that you know, state them precisely. Again, reciting these flashcards can really help you to not make those kind of mistakes. Okay? All right, so that's that example. Here's another one. Let's let S be equal to the real numbers cross with a single point A. So where A, which is an element of R, is fixed. So we fix a real number A, and we form R cross with A. Okay? My question here is, will that be countable or uncountable? Sarah thinks it's uncountable. Noel thinks it's uncountable. What do you think, Saul?
I think it's countable, but put a name on R.
Okay.
That all depends.
Anybody else want to vote? A is just some number. A is just some number. It's like pi or 2.6 or just some fixed real number. It's not changing. It's just some constant number in the real numbers. Uncountable? I think the uncountables have it. So you see that real numbers in there and you're thinking, oh, that's my best example of an uncountable set. So you tend to want to just assume it's uncountable. But be careful, because on the quiz, remember, you had a function from R to R. Some people said, oh, that's I think it was asking you about the range of the function. And people just said it was uncountable because R is uncountable. They weren't looking at, well, the range is not the whole R, right? So just because you see a real number somewhere in the question doesn't automatically make your set uncountable. But in this case, you guys are right. This is an uncountable set. How would I prove it? How would I justify it? Create a bijection. That sounds great. Create a bijection. So I'm going to give the reason up here. Define a bijection, F. Can I call it F? Okay, going from what to what, Noel?
You can go from S to R.
From S to R. Okay, good. If we are able to do this, then because R is uncountable, S will be uncountable. So via, so what is your function going to do? You're going to take an element of S, which is what? It's some real number, comma, little a, right? The elements of S would look like that. X is just some real number. A is this fixed number. And what would be the output, a single real number that you would want to spit out here? Exactly. You just spit out X. Very, very easy to see. I don't even think I'm going to do it right now. It's easy to check that this is a bijection. Okay? Easy to check one-to-one and onto. So I won't do it. I'll save myself that time. So it's a bijection. So since F is a bijection and R is uncountable, so is S, which basically S twiddles R. S twiddles R. So if one side is uncountable, then so is the other side. That's also by a proposition from class. Sarah?
Can we also say that if we assume that S is countable and we have R
So this whole thing would be count if you do like by contradiction or something.
Yeah.
So you assume this whole thing is countable.
That means R is countable.
We never really proved that, did we? We never really proved that if A cross B is countable, that both A and B have to be countable. Those things are true, but they haven't been proved. So I would have to. I wonder how I would handle that. It's kind of obvious. But what we proved in the homework was that if A and B are countable, then their cross product is countable. But you're trying to say something different. You're trying to say, well, if I know that the cross product is countable, then I want to say the individual parts are countable in that cross product. And that we have not actually ever formally proven. So you might need to explain it.
We used that in the quiz in the first example.
I don't think so. I'd have to look at what the quiz was, but I don't think it was necessary to use. So there was a cross product in the quiz. I don't remember it.
It was R.
Oh, R cross. Oh, that was R cross N cross Z or something.
Yeah.
Or no, it was Q. Wasn't it Q?
Yeah.
Okay, this is different. This is different because this is countable, and this is countable. Therefore, all three are countable. That we have proved. But you're trying to do the opposite. You're trying to say, assume the whole thing is countable, and then you want to conclude that the individual parts are countable. You actually can do that. You could prove it. You could prove that if A cross B is countable, then A is countable and B is countable. That actually make a very nice little exercise. Okay, now that I think about it. But that's something we haven't actually ever proved before.
You can still do it by computation and just use the same proof that R is uncountable.
Mm-hmm.
To prove that, like you do by computation.
Oh, yeah. Assume that this is countable and then do the Cantor diagonalization thing where you just have an extra slot that has an A in it everywhere. Yeah, you could do that too. You could do that too. That's a good point. That's a good point. Okay. All right, let's go on to something else here. Okay, so number 3. Let S be the set n plus 2 divided by 3n minus 1 such that n is an element of the natural numbers. Okay, and let's try to compute the supremum of S and the infimum of S for this. And not only compute them, let's actually try to sort of at least prove something about that, okay? So if you saw a question like this is basically a sequence of terms. By the way, because it's a sequence of terms, it's countable. This is countable. You could create a function from n to s where you just say f of n equals n plus 2 over 3n minus 1, and that would be a bijection. So you could therefore say that S is countable, but that's just following up on the previous example. So in this case, how do you suggest we proceed with this? What would you want to do? If you're taking the test, what are you going to do here?
Maybe we're going to try to plug in with the natural number and see if the limit goes to infinity or a specific number.
So plug in some numbers. Just get the idea. I think that's a great thing to do when you don't know for sure what's happening. Plug in some natural numbers into the expression and let's see what we get. Okay? So in this case, when I plug in n equals 1, I'm going to get 3 over 2. Okay? That's the first term. Then when n is equal to 2, I'm going to get 4 over 5. Right? When n is equal to 3, I'm going to get 5 over 8. So the numerators are going up by 1, and the denominators are going up by 3. So 3 halves, 4 fifths, 5 eighths, 6 elevenths, 7 14ths, and just keeps going like that. 8 17ths,